Hey everyone, and welcome to this explainer. Today, we're diving into something absolutely crucial. Really, one of the most fundamental and powerful concepts in software engineering. We're going to explore C++ object relationships, specifically focusing on inheritance and composition. Think of it kind of like learning how to build a digital family tree. We're going to look at how we can structure our code so that objects can inherit traits from one another, just like we inherit genetic traits from our parents. It's a totally foundational topic, and honestly, it completely changes how you approach writing software. So let's kick things off with a bit of a logical puzzle, right? Imagine you're building a massive application for a company. You write this really complex class for a person. It's got a name, an age, a date of birth, and all the functions needed to process that data. Then, your boss taps you on the shoulder and says you need an employee class. Well, an employee obviously has a name, an age, and a date of birth, plus a salary and an employee ID. Are you seriously going to copy and paste all that person code into your brand new employee class? That is a maintenance nightmare. I mean, if you need to fix a bug in how ages are calculated later, you suddenly have to fix it in 2, 10, or maybe 100 different places. We definitely need a better way. Well, that better way is exactly what we call inheritance. Formally speaking, inheritance establishes what we call an is-a relationship. Just like an employee is a person, inheritance lets us create brand new classes, which we call derived classes, from existing ones known as base classes. The really cool part is that the derived class automatically inherits the data members and the functions of its base class. This is an incredibly powerful concept. It drastically reduces software complexity because it lets us write the code once and reuse it naturally wherever that is-a relationship exists. As you'll see here, inheritance basically forms this beautiful tree-like hierarchy. At the very top, we have our base class, shape. It holds the universal, big-picture concepts of what a shape actually is. Flowing down from it, we have our derived classes, circle and rectangle. A circle is a shape. A rectangle is a shape. They inherit the core properties of the shape class, but then they specialize. And it can go even further. Look at square branching right off from rectangle. This tree structure, that's exactly how you should be visualizing class hierarchies in your mind. Okay, moving on to section 1, the is-a code relationship. Now, what's really interesting is how simple this theoretical family tree looks when we actually write it out in C++. Taking a look at the base class side, we have a point with an x and y coordinate, pretty standard. But look over at the derived circle class. Check out the very first line, class circle, public point. That single colon followed by public point is the magic right there. It literally tells the compiler, hey, a circle is a point, just with some extra stuff added on. The circle class automatically gets everything that was public in the point class, and all it has to do is add its own specialized property, which in this case is the radius, denoted by the letter R. But wait, what's actually happening behind the scenes in your computer's memory? It's kind of brilliant, actually. Notice this layout. When you create an object of the derived circle class, labeled C here, it's not just holding a radius floating in space. The base class, that point object with its x and y variables, literally lives inside the new circle object. They are physically bundled together in memory. The derived class totally encapsulates the base class into one complete package. Right, let's get into section 2, the rules of the house, access specifiers. So when you inherit from a base class, you use an access specifier, either public, protected, or private. Think of it kind of like a filter. If you use public inheritance, which is by far the most common, things stay relatively straightforward. Public members of the base class stay public in the derived class. However, and this is highly, highly important, the private members of the base class are always hidden from the derived class. Even though they exist in memory, as we literally just saw, the derived class cannot touch them directly. They are strictly locked away by the base class. So you might be wondering, what happens if a base class wants to share data with its derived classes, but keep it completely hidden from the rest of the outside world? That is exactly where the protected keyword comes in. If you declare members as protected in the base class, they act just like private members to anyone outside the family, meaning main or other random classes can't touch them at all, but they are fully accessible to any derived class. It's basically the perfect middle ground for a family secret. Next up is section 3, the life cycle, focusing on construction and destruction. Think about it like this. You literally cannot build a house without laying down the foundation first, right? Well, C++ feels exactly the same way. When an instance of a derived class is created, the compiler enforces a very strict order. Step 1. The constructor of the base class is called first. The foundation has to exist. Step 2. If the class is composed of other member objects, let's say a car class that has a separate engine object inside of it, those constructors are called next. And finally, step 3, the constructor of the derived class itself is called to add those finishing, specialized touches. It always builds from the inside out. And then, when it's time for that object's life to end, the teardown process is just as strict, but it runs in reverse. Destructors execute in the exact opposite order. 3, 2, 1. The derived class's destructor runs first, stripping away all the specialized additions. Then any member object destructors fire. Finally, the base class destructor runs, clearing away the foundation. This ensures the derived class can safely clean up its own messes before the base class it relies on is pulled out from underneath it. Moving right along to section 4, carving new paths, dominating and overriding. So we've seen how a derived class builds upon a base class. But children aren't always just exact clones of their parents, are they? Sometimes they develop their own behaviors, or they rebel entirely. In C++, derived classes do this through dominating and overriding base class members. Now, these are two distinct concepts that get confused all the time. Dominating happens when a derived class creates a variable with the exact same name as one in the base class, essentially hiding the parent's variable. It also happens if the derived class creates a function with the same name but a totally different parameter list, which we call overloading. Overriding, on the other hand, is when the derived class completely redefines a base class function. For it to be a true override, the function absolutely must have the exact same name, the exact same number of parameters, and the exact same types of parameters. It is a total replacement of behavior. Let's actually look at how this plays out in code. Over on the left, we see dominating in action. Class Y inherits from class X, but class Y defines a function H that takes a character array, while the base class H takes a float. Because they share the name but have totally different parameters, class Y is dominating or hiding that original function. On the right side, we see true overriding. Look closely at the function OV taking an integer I in the base class, and OV taking an integer K in the derived class. They have the same name and the same integer parameter type. Class Y has completely overwritten class X's version of that function. Now you might be wondering, what if I completely overrode a function, but somewhere deep inside my new derived logic, I suddenly realize I still desperately need to call my parent's original version? Well, you aren't locked out. You can just use the scope resolution operator, which is literally just 2 colons. By typing the base class name, function name, you bypass the override entirely and force the compiler to use the original hidden base class version. It's a super handy loophole for when a child class just needs a little bit of help from the parent. Finally, let's zoom out a bit for section 5, the big picture of object-oriented design. We've been super deep in the syntax weeds, colons, access specifiers, destructors, all that. But stepping back for a second, how does all of this fit into the grand philosophy of software engineering? It all comes down to object-oriented design, or OOD, which rests on 3 massive pillars. First up is encapsulation, tying data and the operations that use that data tightly together into a single unit, a class. Second is inheritance, which we just mastered, creating new classes from existing ones to eliminate redundancy and build logical hierarchies. And third is polymorphism, which is this incredible ability to use a single interface for many different underlying forms, like treating a circle and a rectangle simply as shapes in your code. Inheritance isn't just some neat trick. It's the actual bridge that connects encapsulation directly to polymorphism. So I want to leave you with a quick thought experiment. Look at the project you're coding right now. Are you writing the same variables and the exact same functions over and over across slightly different files? If inheritance allows us to build these elegant family trees of code, efficiently passing down traits and redefining behaviors only when we actually need to, how much redundant code could you go in and delete today? Master inheritance, and you don't just write code, you design elegant, highly scalable systems. Thank you so much for hanging out with me in this explainer, and I'll catch you in the next one.